Hey, AP Chemsters, this is Mrs. Vandelay bringing you Blankwalle 6.3. This is the first law of thermodynamics, otherwise known as there is no free lunch. And what does that mean? Well, the total energy of the universe is constant. So why is there no free lunch? Well, usually that is a saying that means you don't get something for nothing. And so because the total energy of the universe is constant, if you lose energy, then something's going to gain it. Or if you gain energy, then something's going to lose it. So it's a give and take. There's no free energy, if you will, in this case, okay? We'll talk about what Willard Gibbs called free energy down the road, but not right now. So anyway, it says, since energy is neither created nor destroyed, since the universe does not exchange energy with anything else, its energy does not change. You cannot get something for nothing. So there is something called internal energy. We talked about this in section 6.2. Again, internal energy is the sum of all the kinetic energy, which means your motion, and potential. What did we learn in the section 6.2? Potential is your bond energies of all the particles that compose a system. Now, this next one is important. Internal energy is what's called a state function. It depends only on the state of the system, not how it arrived at that state. So a state function, will you write this down, please? It depends only on where you start and where you end. It doesn't make any difference which path you go in. And again, this is something that we're going to practice later on in this unit and really delve into that. But for right now, let's see what a state function is in pictures. So remember what I said, a state function, it does not depend on how you get there. It only depends on where you start and where you end up. So if you check path A, all right, you start here at the bottom and you go zigzaggy your way back up and you hit to the top. It took you 12 miles, all right? If you are an experienced climber, maybe you take the direct route up, but you still start at the same place at the bottom and you still end in the same place at the top. And you both went a total of 1,000 feet vertical. However, somebody took a lot longer pathway to get there than someone else, all right? So right here it says a state function, change in altitude depends only on the difference between the initial and final values, not on the path taken. Okay, that is a state function. Let's go to the next page. So this is a Mrs. Vandelwalle analogy here. When I think of state functions, I grew up watching, or not watching, but looking at the newspaper and saw the Family Circus cartoons. I don't know if you've ever seen the Family Circus, but this shows up a lot. So what shows up here? He starts in bed. He jumps out. Notice the arrows going this way. He goes all around and he goes up the hill. He races somebody. He goes over Humpty Dumpty's wall. He goes around here, goes through Mary's garden, seesaws with something, climbs a tree, comes around, see little Bo Peep's sheep, come bounce, 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 goes around here, and he's back in bed, okay? So where did he begin? In bed. Where did he end up? In bed. So how did he get there? He could have stayed in bed, or he could have done all these other things, and then he says, my legs are tired. So anyway, that's another idea of a state function. Where you began, where you end up, wherever, how you got there makes no difference, okay? Not in a state function, okay? Let's go on. Okay, so problem number 2 says, describe how the following statement describes a state function. It says a liter of water behind a dam has the same potential energy for work regardless of whether it flowed downhill to the dam or is taken up to the dam in a bucket. So why don't you use a little bit of time right here, pause this, and write down what you think is going on here. So when you're ready, come back and join me. All right, welcome back. So this is how I would probably word it. Where is that water? It's behind the dam, okay? Does it make any difference how it got there? Not at all. Did it flow down? Did it get carried up? It makes no difference. The only point is where it is right now, and it has the same potential energy from work. So it's all going to go the same place to do that work. So the final place and the beginning place is all that matters. It doesn't matter how it got there, okay? Now, you will see this is important right here. We're going to use this. So delta E is E final minus E initial. How else can you write it? So in a chemical reaction, what's my final? It's my products. In a chemical reaction, what's my initial? It's my reactants, okay? So this is important. Delta always means final minus initial. So delta temperature is final temperature minus initial temperature. So delta E is final energy minus initial energy. So if I go back in section 6.2, let's do that real quick. You remember this right here? All right, so what would be my delta E? What's my final? It looks like 1. What's my initial? It looks like 2. So what's 1 minus 2 is -1. So your delta E for this system here is going to be -1. Final minus initial, okay? And we're going to talk about this more, but that negative sign is really important. Because where did that energy go? It went from the system to the surroundings. Notice how your surroundings got more? That negative tells me that the system gave energy to its surroundings. Okay, so let's go back to section 6.3. So delta E can be positive or negative, and I've already kind of referred using that picture from section 6.2 what I'm talking about. So if delta E is negative, okay? What does that mean? Go back to that first page. What's bigger, your initial energy or your final energy? Look back on page 2. All right, hopefully you said your initial energy is greater than your final energy. Do you remember how on page 2 the initial energy was 2, the final was 1? Okay, what is this graph going to look like? Well, here's my graph of energy versus time. And so if I start off where the initial energy is higher, right, than my final, so isn't it going to do something like this? Yes. All right. And so what can I say here? Final minus initial. I don't care what the numbers was. I used 1 and 2 last time. But if I have a lower number minus a bigger number, isn't that always a negative number? And what did that mean? Energy has been lost. Okay, where did it lose? To the surroundings. Okay, so let's see what happens when delta E is positive. So this is really the opposite of what we just did, okay? So if delta E is positive, that means your final is greater than your initial, okay? So what would a graph like this be? Your final is bigger than your initial, right? So here I have a low initial, like maybe 1. Your final is bigger, like maybe 2. All right, and so look at what happens here. Your arrow's going up, isn't it? Okay, so this is an upward trend. So again, final minus initial is a positive number. Well, how did the final get to be such a high number? All right, why is this higher than where I began? Well, because, your system gained energy. How did it go from here to up here? You gained energy. So if I want to, roll a ball up a hill, how does the ball get up the hill? I have to give it energy to go up the hill. So if it starts lower, I gain energy to get it higher, okay? These graphs are really important, okay? So make sure that you have this visual. Go back and look at it again if you need to. Go back and listen to this recording if you need to. But this is really a key idea in understanding this chapter, okay? Let's see what else is going on here. So it says summarizing energy flow. Oh, you must know this, okay? Commit this to memory if it doesn't make sense, all right? If you can't figure this out, if you can't reason it out, just memorize it, okay? If the reactants have a higher internal energy than the products and the delta E, the change in the energy of the system is called negative, and the energy flows out of the system to the surroundings. That's like what we saw on the first page of your notes in section 6.2. If the reactants have a lower internal energy than the products, the delta E system is positive. Energy flows into the system from the surroundings. So it says problem number 3, consider this. Okay, This is your, again, your gauges for your chemical system and the surroundings, okay? So which diagram best represents the energy gauge for the same system and surroundings following what? An energy exchange where the E system is negative. Okay, so let's check this out. What does that mean if delta E is negative? If you need to go back and look it up, then so be it. But if it is negative, that means it lost energy to the surroundings. So which one of these is showing that the system lost energy to the surroundings, okay? So system has to go down, surroundings has to go up. Remember, we always have to have the same amount of energy as before. So if I have my 3 plus 1 is 4, I have to end up with 4, right? So this is going to lose. So where does it go down? Well, it looks like A and B went down, C went up. That doesn't make any sense. What about your surroundings? Your surroundings has to go up. Well, here your surroundings went up, here your surroundings didn't do anything, and here your surroundings went down. So which one is it going to be? It's going to be A. Okay, and what else would be a good check? Add them up. 2 plus 2 is still 4, just like here. So that still fulfills the law of conservation of energy. So the question is, how can a system and surroundings exchange energy? It says through heat and work. Let's go back and revisit a definition, will you? So I'm back on page 1 again. A lot of good stuff on page 1. And we defined energy right here is the ability to do work and or produce heat. That is a definition that the physicists and the chemists all agree on. The ability to do work and produce heat. So let's go back and see what's happening in section 6.3 again. How can a system and surroundings exchange energy? Through heat and work. So heat is defined or is abbreviated as the letter Q, means quantity of heat, and work is W. So notice that there's always this exchange between the system and the surroundings. So delta E is equal to Q plus W, the heat plus work. All right, so here we have heat. If it is positive, that means the system gains thermal energy. That means it's getting warmer. The system's getting warmer. If it's negative, that means the system loses energy and the system will get colder. Why? Because it's giving its energy to the surroundings. But work. If it's positive, work is done on the system, and if it's negative, work is done by the system. Do you remember on that first activity we did to start this unit, you had that piston, you had a syringe, I should say, you had a syringe, and you're pushing in on it, okay? When you put your hand on it and push that syringe down, that meant work was positive. Work was done on the system. And then when you released it and that syringe pushed back up, that means the work was done by the system to your hand, if you will. Okay, so go back and revisit what we did in that first day of those stations that we had. We were talking about this exact same thing. So if the internal energy change is positive, that means you have a net positive energy flow in the system. If you have a delta E is negative, you have a net energy flowing out of the system. Now you can have Q being positive and work being negative, but whichever one's bigger will determine then what the delta E is going to be. All right, so let's kind of see, there's some examples here. All right. When does a system gain thermal energy? Well, when ice does what? When ice melts, okay? What's something that will lose thermal energy? It'd be like a candle giving off heat to its surroundings, okay? What about your work being done on the system is when you push that syringe in, and when was work done by the system is when the syringe pushed out onto your hand, okay? So I'm going to leave you with this to start with. We have more, don't worry. But I put this star here for a reason. Oh boy, oh boy, oh boy, is this ever an important thing to just sit down and try to memorize or try to make sense of, okay? I'm trying to give you ways to think about it, But, you know, in the end, all right, it's a state function. In the end, doesn't matter how you get there, you have to know this, okay? So I'm going to leave you right now. Don't wait to be great. We'll see you next time. Bye-bye.